Hello and welcome to this lecture. My name is Kobi Schondorf and I will be giving you this first lecture. And in this lecture we're going to talk about the scientific background and the background foundations to NeuroVision science. Let's start with some things that are very easy and trivial, but sometimes not that obvious. How do we see? And our vision depends on two things, which is the way the eye receives the images, which we call the front end of the image of the vision system, which actually starts with the light falling at the cornea and ends at the retina of the eye, and the back end of the visual system, which is the brain that actually interprets the image that it receives from the eye and creates a perception. So in our vision, actually, our visual system works in a way that the object is perceived in the eye, which is the optics of the visual system, continues to the brain, which is kind of a processor that understands the information and creates a perceived image. The eye industry would traditionally focus on the front end of the system, on the eye, and on bending the light and making sure that the light falls properly on the retina, while NeuroVision actually doesn't treat the eye, but it looks into the back end of the system, at the brain, at the processor, and it's optimizing the processing, the visual processing that happens in the brain. The improvement that we can receive or achieve in the NeuroVision treatment is equivalent to up to 1.5 diopters of spherical blur and 75 diopters of astigmatism or cylinder blur. So this is the kind of improvement in vision that we can achieve with NeuroVision while focusing on the back end of the visual system. So what NeuroVision actually does, it trains the brain to automatically sharpen the image. This is very similar to the way a computer software enhances a low-resolution image. You can think of a camera image that is in low resolution or not optimal or a little bit blurred. Then you can take Photoshop to improve the output or the outcome of that photo. Similarly, NeuroVision is kind of a Photoshop to the brain. It makes the brain work in a more efficient way and enhances the processing and improves the perception. So now that we understand that NeuroVision actually looks into the back end of the visual system and the way the perception is created in the brain, let's try to look a bit into the science and understand what actually happens in the brain and how does NeuroVision improves that. The terms that you need to be familiar with and that you will find in the NeuroVision technology are the first building blocks, the Gabor patches, which I will demonstrate to you shortly. Then we'll talk a bit about neural lateral interactions that happen in the brain. We'll talk about neural plasticity or plasticity in the brain and about a process called perceptual learning. Let's start with Gabor patches. Gabor patches are the patterns that you see here on the right side. These are called Gabor patches and they follow a formula actually invented by Dennis Gabor, who was by the way, Nobel Prize winner for inventing the holograms. But these are very widely used as the building block of visual neuroscience. Scientists in this field of visual neuroscience have shown that these Gabor patches efficiently describe the receptive fields of neural cells in the primary visual cortex. NeuroVision focus on the primary visual cortex, what we call V1, the first area in the brain that actually receives the information from the eye, and that has some tens of thousands of neural cells. Each one is filtering a specific type of Gabor patch, like the one shown here on this slide. What actually happens in the brain is that when these neural cells that you can see here on the diagram on the right side are stimulated by a visual stimuli, it creates some activity in the visual cortex, and these are interacting together. Those, for example, neural cells that are all filtering horizontal stimuli. So you can see there is some activities there, and they are interacting together in what we call lateral interactions along some axis to create a perception, to create some activation that tells the brain there is some information here. So those, what you can see here on the left side is that those individual neurons are actually filtering precise location, orientation, and spatial frequencies. So different Gabor patches that are located in different places around us that may have different orientations. Some may be vertical, some may be diagonal, some may be horizontal, or have different spatial frequencies. If I go back for a bit, these can be very wide Gabor patches with what we call low spatial frequencies, or very dense, very narrow Gabor patches with a very high spatial frequency. So these neural cells will actually filter different stimuli according to these parameters here. The basis to NeuroVision is actually started with what we call the cat visual cortex experiment, which was published in the Nature magazine in 1998, which initially showed that when you measure the activity in a neural cell, in this experiment in a cat's brain, you can see that as the contrast of the Gabor patch grows, this is the horizontal axis, the response, the neural activity, or actually electrical activity in the brain increases, and that happens in a very well expected way. The amazing thing found in this experiment was when actually there were 3 Gabor patches all presented together, while we were actually measuring the response to the central one. You can see here it's very fade at the beginning, and the contrast of the central one is increased in this experiment. You can see the green line that actually shows the response to a single Gabor patch as a reference, and you can see that while we introduce a Gabor patch above it or below it, the response of the central one is actually increased. And by the way, this is shown only when they are all aligned vertically like that. If we will put those at the sides in horizontal orientation or diagonal or some random orientation, we will just measure exactly the green line again, to have this facilitation effect, which means that suddenly this area is more sensitive. The response is much stronger because of the introduction of those Gabors at the sides. Will happen only if they are all laterally arranged along the same axis, like in this example. So we saw with a cat experiment that actually with special arrangement of Gabor patches in space, we can increase the sensitivity or increase the response of neural cells to weaker stimuli. Now we look into the concept of neural plasticity, which actually relates to the ability of the neural system in the brain to adapt to changing conditions, which is in acquiring new skills. So not only that we can increase the sensitivity, we can actually make the neural system acquire this new sensitivity, make it more sensitive, and make that skill retained for years, just like somebody who learns how to ride bicycles or learn how to swim, which is also a skill acquisition that is retained for years. Similarly, we can increase the sensitivity of neural cells in the brain in a methodological way, which I will introduce, and make sure that that new skill will be retained for years. And we see that evidence for neural plasticity even in adults in many case studies and many publications, and you can see here just a list of references in this slide, just like prolonged patching for amblyopia, or amblyopia where the better eye vision was lost due to AMD, cataract trauma, and such. The concept of perceptual learning actually shows that performance can be improved with proper training. This is quite straightforward if you think about somebody going to a gym or doing a diet. Of course, that by training you can improve performance, but when we look at very basic skills like visual performance, or you would think audio detecting performance, you would think that individuals just have some level of skill ability that cannot be improved anymore. Neuroscientists showed that with perceptual learning and very methodological training, you can actually improve very low-level brain skills such as visual performance. And this is exactly what we do with NeuroVision. We use repetitive performance of controlled and very specific visual tasks, which, when doing that repeatedly in a very controlled way, in very controlled parameters, we see improvement in performance in different visual tasks, and that was found to be persistent for years. By the way, not only in NeuroVision, some other scientists showed some other kind of visual tasks like visual attention or vernier acuity that was persistent for years. This whole field of visual perceptual learning is very solid in the discipline of visual neuroscience. So what do we actually do in NeuroVision? We enhance neural lateral interactions using the perceptual learning technique. We're doing repetitive performance of specific visual tasks, which effectively stimulates specific neurons and increase the sensitivity of these neurons by promoting spatial interactions among these neurons. We create stronger connections between laterally arranged neurons and thus increasing the sensitivity of these neurons. In more engineering terms, we will say we reduce the noise level in this neural activity and increase the signal strength. In more simple words, we increase the ability to detect weak signals. We increase the ability to detect low contrast. So if some information appears somewhere, even in very low contrast, someone who does the NeuroVision treatment will be able to detect it, even if the information contrast is quite low. Therefore, what we do is we improve the efficiency, or actually improve the contrast sensitivity or the contrast sensitivity function. Improvement in contrast sensitivity also induces improvement in visual acuity. So NeuroVision actually increases sensitivity of neural cells in the primary visual cortex in V1, increasing the signal strength, increasing the sensitivity to low contrast, thus increasing the overall contrast sensitivity function and improving the visual acuity. So to summarize this lecture, our vision quality or our image quality depends on both the quality of visual processing, so to say, at the eye. Any refractive error will definitely make the image blur, but not only the things that happen in the eye, also the processing that happens in the visual cortex. The visual system in the brain has mechanisms to further enhance the visual processing. We can Photoshop the information. We can upgrade that Photoshop that we have in the brain by using those lateral interactions between neural cells in the primary visual cortex. That neural processing efficiency can be further enhanced in most people, as it is yet not fully optimized. So you don't need to have amblyopia to have some issues with the visual system in the brain. Each one of us has some room for further optimizations and increase of functionality in our visual cortex. For those with amblyopia, what we actually do in NeuroVision, we enhance the neural processing to better process the clear image from the retina, and thus to create normal image. So we take fully corrected image from the retina and try to create normal processing in the brain in order to achieve normal acuity or close to normal visual acuity. In our other applications, such as myopia, presbyopia, post-LASIK or post-cataract, actually we compensate for blur inputs coming from the retina. And this way, it's not an issue with an amblyope who has a visual system in the brain that didn't develop properly during childhood, but rather we have a normal visual system, but we have less a normal quality of vision coming from the eye due to myopia, presbyopia or such. What we're doing is we're photoshopping the information that came from the eye to make it sharper. So despite the fact that there is some level of blur, up to about 1.5 diopters, as I said previously in this lecture, we can compensate for that using NeuroVision, so the brain can actually perceive normal acuity or close to normal acuity despite the blur information that was received from the eye, and thus creating an optimal brain processing mechanisms to process those visual signals even better than the average.